So we're gonna wait a couple seconds because there's some people stuck in the waiting room. But we're gonna be talking about recursion today. But before we really talk about it, in case you guys didn't know, the next USACO contest is like this weekend. It's January 22nd to 25th. So that's like Friday to Sunday. And it basically opens up at like 12 a.m. on Friday. I think it's Eastern time, but I'm actually not sure. So just like a quick refresher, just all you need to do is just log in or create an account if you don't have one yet. And then on the day of the competition, the site will change. And instead of this thing here, it will say something like January 2021 contest or something. And then there'll be a start button if you're logged in. And then you probably have 4 hours. It might change. It's normally 4 hours to do normally 3 questions. And that's about it. The new changes from this season, right, were there are no templating allowed. Basically, everything you write has to be from scratch. So if you memorize your template, that's also fine, but you just like can't have it pre-written out before the contest. And then also, instead of file input output, it's going to be system input output, I believe. So basically, you don't need to like worry about files anymore. And then also, if you like have any questions about the problems like during the contest, you can't ask anyone about it, like the general programming questions. You can't Google anything though. That's totally fine. But if you have like questions about like technical difficulties, like let's say your submission's not working or something, you can message one of us. Or what's probably better is you can message like uh, this guy right here, Dr. Brian Dean. He's the guy who runs it, so you could probably email him. Though you might not get a response in time because like you have a 4 hour block. So yeah, that's like a risk. But basically that's it. If you're done with the contest, you're technically not allowed to discuss with anyone else about it. But yeah, that's about it. Um, so now to continue on with the lesson. So just really quickly, we're gonna use the example of like a Russian doll. So you guys have probably seen one of these before, but when you open it up, there's like another one inside that's like a bit smaller, right? Like, so this is like the cap of this one. I mean, it's kind of hard to explain unless like you guys have seen it before. So hopefully you guys have. But basically it keeps on going until you have like three, four, and then to the point where you have like a lot of these very small um dolls. Yeah. And then basically this is like an infinite loop, right? Because you keep on going smaller and smaller. However, um, just like for the sake of argument, we're not gonna like assume like about particles and stuff. But basically there's gonna be a point in time when the doll is so small that you cannot fit another one inside. And that's the part when like it breaks and when your loop basically finishes. And that's how recursion basically works. It's very similar. With recursion, you're aiming to solve a problem by solving smaller instances of the same problem until the problem is so small that it can be solved automatically, basically. If it's confusing, it'll make more sense when we visualize it and actually like code it up really quickly. But that's roughly how it works using this like Russian doll example. And then just some like quick bullet points. So a recursion is it's a function that calls itself until a base condition, right? Like a base condition was like earlier in the Russian doll example was when it was too small. But until a base condition is true, then it stops. So it's basically an infinite loop that's a function until a base condition is true. And then also another thing that's important when you're programming recursion or in programming in general, if you ever get a stack overflow error, so like in Java, it might be like a java.lane.stack overflow error, I think. Um, like basically 99% of the time, that means that you have a infinite recursion loop, or there's too many recursive function calls. Because how it works is that each time you call a recursive function or you call a function, it's being pushed onto a stack, which like stores like your data and it stores like memory and stuff like that, whatever. But basically, the stack has like a limit. So like once you overflow that stack limit, your program's gonna break. And most of the time, it's something to do with your code. It should be like a pretty simple bug to fix. And then also one neat Easter egg is from Google. So if you guys didn't know, But if you go ahead and Google recursion, it has this like top, like, did you mean recursion, right? And this is normally like a spelling error type thing. But if you notice, like, we didn't spell it wrong, it's spelled perfectly fine. So when you click on it, it just takes you to the same page and you keep on clicking it. So it's kind of like an infinite loop. So that's roughly how it works. So now I think I'm going to stop sharing and Zenkai is going to continue with like a demonstration about recursion. But if you're like a bit confused on how it works, that's also fine because it'll make more sense in a bit later.
So to illustrate like how recursion, okay, this class name is messed up. Okay, to illustrate how recursion works, I'm gonna do a demo on Fibonacci, the Fibonacci sequence. So basically, our task is to create a function that returns the nth number in the Fibonacci sequence. And if you don't know what the Fibonacci sequence is, it's basically a number sequence that looks like this. 2, 3, 5, 8. So and so on. So basically, each number is the sum of the previous two numbers. So that's basically how this works. And this is pretty easy to solve with recursion. And so basically, the base condition for the recursive function is that if n is equal to 1 or 2 or 3, we can just return the corresponding solution. And if it's larger than that, then we can, we can do a recursion and basically return the we can call the function on so basically call fib n minus 1 and then add it and then add fib n minus 2 and that will give us fib of n. So basically this is the implementation. Yeah, so some sources say that Fibonacci sequence doesn't have the 0, but I'm gonna include it anyway because it makes more sense. So the first when n is equal to 1, we return 0, and when n is anything other, when n is 2 and 3, we return 1, and for all other cases, we need recursion, so we return the sum of the previous two terms of the sequence. So that's basically how it works. And to make it clear, we can do a visual demo of this. Gosh. So okay, for n of 5, let's see what it looks like. So basically, when you call fib of 5, it will call fib of 4 and fib of 3 and add them up. And then each of these functions each of these function calls is going to do the same thing. Fib of 4 is going to call fib of 3 and fib and add it to fib of 2. I mean fib of 4 and return it. And yeah, and it just works. And yeah, recursion just works like that. And when you reach the base condition, the simplest problems, we can just return the answers. And we basically combine these solutions and calculate the final answer. So yeah, and so for small numbers of n, this recursive function, it works fine. But for larger and larger numbers, it's going to cause a stack overflow. So in order to prevent that, we can unroll this recursion and we can unroll, yeah, yeah, whatever. We can unroll this recursion and then optimize it. So yeah, here is a non-recursive version of the same function. So yeah, we still have the base cases. These are the same. We don't want to calculate them because we already know the solutions to them. But but instead, for all other cases, instead of calling itself, we instead use a for loop to emulate the process. So we have the n-1 right here, A, and we have n-2 here, which is B. And we also have a temporary variable for setting the sum. Okay, so basically we add A to B and save it into temp, and then yeah, so and then we make wait, how do I describe it in words? So okay, basically we emulate the process of manually adding the previous two numbers and then making it a new term, and then adding the previous two numbers and adding the new term, and that's what this for loop does. And that's all it is. And after I reaches n, after we reach the nth element of the sequence, we return B. Yeah, that's basically it. And so that's it for Fibonacci sequence. We also have a more complicated example. We won't. We might have time for that. Yeah, I'm gonna try anyway. So we have a USACO problem. This is a silver problem, and so you're given a n by n matrix like this. So you have a bunch of a few rows of characters, and if you have a sharp or whatever or a pound symbol, I guess, it means that it's an ice cream. It's this block is filled with ice cream, and you want to find the blob. A blob is basically a contiguous area. It's not a professional term, by the way. The professional term for that is like component, but yeah, we use the term blob to ease understanding. So you want to find the blob that has the maximum contiguous area of ice cream. So, but if multiple blobs have the same area, then you want to choose the one that has the least perimeter, and your task is to find this blob and then output its area and perimeter in this file. So what we can do is we can use an algorithm that uses recursion called flood fill, and this flood fill algorithm also uses is a form of depth first search, but you don't have to worry about that right now. So basically, we start from the top left corner, and then we mark it as visited in the visited array, and then we add its area. And then we keep track of the area of the current blob, and we can find the perimeter by counting the empty cells next to it. So from the current cell, we add one to area. We check if the surrounding cells are empty, and if they are, we add a 1 to the perimeter for each of them. So 1, 2, 3, and then we call the same function. We call the search function, or basically you visit, and then we visit the next cells. So from this cell, we'll sequentially visit this cell and then this cell, and this will continue for recursively for the rest of the cells. And by the way, we only visit the cells that are filled with ice cream. So let's look at the implementation. So the main function. So this is C++, but there's not much difference other than how you do I/O. So CIN is like scanner, but you don't have to initialize it. It's already there. You just have to replace it with you have to reopen the input stream and output stream with using the corresponding file. And don't worry about this right here. And so the first step, you get the number n from the input stream, and then you process all these characters on the matrix. And then, yeah, so that's basically input output. Okay, that's basically input processing, so not much interest there. And then we create, so this blob variable keeps track of the current blob we are on. So, and then for each blob, we keep track of its area and perimeter. And then we do we visit the first cell of this blob. Okay, you might wonder how we make sure that the cell is not okay, you might be wondering how do we make sure that the cell we visit is not already a part of the is not already a part of wait, how do I describe it? Okay. So okay, basically we loop over all elements of this matrix, all cells of this matrix, and then okay, in each visit, so every time we call the DFS function, it will visit all blobs. It will visit all cells in this blob, and then it will mark them as visited. So after this current iteration, so after this current iteration, it will continue to the next iteration, and it will skip all of those that are visited, and that are it will skip all of those that are not an ice cream cell and are not and are visited, basically. So yeah, that's all there is to it. But so let me show the DFS function. So as always, if this current cell is visited, we'll return, because we don't want to waste memory and time. And this CMP array or matrix is basically it records the blob number of the cell ij. And by the way, we pass the blob number as an argument. So this is what the blob variable is for. And yeah, for each iteration, so for each blob, we increment the blob number. And remember, the DFS function actually visits all cells of this contiguous blob, and with the help of the visited matrix, we won't visit the same blob again. So yeah, and then we increment its area by 1 because we are visiting one cell, and then we check if the surrounding is empty, or if it's an edge. If it is, then we increment the perimeter of this current blob. I don't have to worry too much about the logic, and we look for, and then after we calculate the perimeter of this current cell, we head on to the next cell by calling DFS on the next on the surrounding cells. So yeah, so if it's an edge, we don't care about it, we skip it. If it's empty, we also skip it, but the DFS function will handle that. It will skip it automatically. And yeah, basically do DFS on all of our 4 surrounding cells. And that's what these are for. Notice that we pass the blob number to the to the DFS call on the surrounding cells because they are contiguous. And that's all there is to it, I guess. And to actually, okay, so after doing the DFS thing, we will have figured out for each blob what area it has and what how much and the value of perimeter it has. So we can figure out the best area and the best perimeter by basically doing a for loop and iterating over all blobs. And you know, it's like the max number in an array algorithm. Okay, there's it's not relevant to the topic of recursion, so I won't go too much into the actual solution. But here you are. Okay, I think I'm done. I'm gonna stop sharing.
Yeah, okay, so we still have like 13 minutes left. Really quickly, there are 2 questions on the HackerRank. If you haven't done it before, just go to this website, and then you also need to create a HackerRank account, by the way, to be able to access our contest. And then it'll either say sign up. If you haven't signed up before, then you click enter contest. And then you're greeted with the past challenges, but we want the newest ones, right? Because these are from lesson 12, which is today. And so there's a factorial problem and a Fibonacci numbers problem. This one Zenkai talked about earlier. The factorial one's really simple, so I'll just quickly go over it. Basically, you really don't need to read any of this. It's just you're given a number and you need to output the factorial, except we're going to be doing it with recursion, right? Because that's the topic. And so normally with factorials, a factorial, if you guys don't know, hopefully you guys do know, but it's basically just like a factorial of n is equal to n times n minus 1 times n minus 2 all the way to like 1, right? And so what that basically is so like factorial, so n factorial is actually equal to n times n minus 1 factorial. And hopefully that makes sense, right? Because we know n factorial is n times n minus 1 times n minus 2 all the way down, and n minus 1 factorial is the same thing, which is without the n. And then so you keep doing that. And then to find n minus 1 factorial, let me put parentheses. This is simply equal to n minus 1 multiplied by n minus 2 factorial. And you keep on going down, right? Until you reach your base case. And you keep on going until you reach like n or whatever number it is equal to 1, which by then you just return 1. So hopefully that makes sense. So the code up our recursive function, everything's given to us. The scanner takes in all the stuff. It calls the function. So we just need to code this part. So the first thing we want to code is our base case. Right? So basically if n, right, which is the argument passed inside a function, if it's equal to 1, we want to return 1. And then if it's not equal to 1, we're just going to return n multiplied by factorial of n minus 1. And then this code should work. So if we run our code, it should work against a sample input, 3 factorial 6. However, if you guys do recall, 0 factorial is equal to 1. So if I put in like 0 as a custom input and run the code, I think it's going to break because, yeah, see, this is a Stack Overflow error I was talking about because it's like an infinite recursion. So basically to solve this, it's pretty simple. There's a lot of ways you can do it. But if we just simply change it to n is equal to 0, return 1, then our special case of 0 factorial should return 1. And so, yeah, that's pretty simple. Hopefully that made sense. It's like a very, very standard recursion problem. You keep on looping until you reach your base case. And then I want to go over the Fibonacci solution. So Zenkai showed this earlier, right? But this is also another recursion, another like visualization website. I just found it easier because it has this thing here, but I already coded up the Fibonacci sequence in here. It's actually a predefined template, but this gives you your recursive Fibonacci sequence. So if we run fn of 5, right? So this will give us the fifth number in our sequence, which should be 5, I believe. So you see it returns 5, right? But you also notice it's kind of slow. And it's kind of slow because we're calculating the same values multiple times. So if you notice, like we're calculating a 2 here, another 2 here, another 2 here, etc. It's actually easier to visualize from here. So hopefully you guys can see my VS Code. So if I go to Fibonacci solution, I added this system.out printf here. Basically, it prints out which Fibonacci number we're computing. So let me quickly. Okay, so if I run this program and I put in 5, right, it actually tells us which ones we're computing. So it starts off, we're computing Fibonacci of 5, right, then 4, then 3. Then you notice we're computing 2, then 2 again, then 3 again, then 2 for the third time. So all of these things here are actually unnecessary, right, because there's no point in computing like the same case again. There's no point in computing Fibonacci of 2 3 times. So instead, you want to do something called like memoization. I have no idea how to pronounce it, but
Memoization.
yeah, what he said. You're gonna view this a Wikipedia article. This is how it's spelled, if you're wondering. But basically, what it is it's a way to solve this error, not error we have, but this like over computation, basically. So a simple way is like you just store the values into an array and you call them from the array if it's like full. But I think like a more conventional method is probably to use a hash map. So if you're unsure what a hash map is, uh, that's kind of unfortunate because I'm not going to explain it too much in depth. But a hash map in Java, it stores a key and a value. In this case, they're both integers, and then so the value is assigned to your key, right? So hopefully that makes sense. So in our case here, right, where we're computing Fibonacci of 2 3 times, right? So the first time we compute Fibonacci of 2, what we want to do is we want to store the answer for Fibonacci of 2, which I think is 1, right? Um, yeah, it should be 1. So we want to store 1 as the value to the key, which is 2. So we want to add in 2, 1, right, as like our little ordered pair, right? The key is 2 because that's the number we're computing, and the answer from that is 1. So it'll make sense when you run the code. But basically, it's identical, right? So we have the two base cases. If n is 0, return 0. N is 1, we want to return 1. And then this is our hash map function, or not function, hash map code. So the hash map is called memo. It's short for the word we were talking about earlier. And then if memo contains key, right? So this is like a method. It returns a Boolean, right? If it contains the key, and then we want to pass in whatever key it is. And note, we initialize both the key and value to be integers. So if memo contains the key, right, which is n, the argument passed, which we're computing. So if it contains it, then we want to grab that number from memo. So we just grab it by doing return memo.get, and then you pass in the key. And once you pass in the key, it'll return you the value that corresponds to that key. And this printf here, it just tells us what we're grabbing. And then assuming memo does not contain the key, right? So let's say we haven't calculated it before. Instead, what we want to do is we want to just recursively call it. So we want to we just a little print statement, same as before. And then this time, instead of just putting return result or return Fibonacci n minus 1 plus Fibonacci of n minus 2, we're going to store this integer answer or whatever this is into an integer called result, just so we can put result into our memo, right, which is our hash map. So then once we calculate this, we're going to put it inside our hash map with the key of n, and the value is result, which we computed. And then we're going to return result as the answer for the whole thing. So now we're going to run this code. So we're going to do 5 again. And then this time you see it's a bit different, right? We're computing Fibonacci of 5, then 4, 3, 2. And instead of recomputing 2 and 3 multiple times, we're just grabbing the value from our hash map and we receive 5. So if we go back to this visualizer and we click enable, we enable the fast method, yeah, memoization or whatever, and we run it again, you'll notice that it doesn't like have all of those extra branches off to the right, which is simply because it's not recalculating the multiple times. And so that's also kind of key to dynamic programming, which we're not talking about, but it's pretty similar and it'll be used over there. And I think that's basically it. I don't have anything else really prepared. So if you guys have like any questions, you can let us know. You can stay behind. Otherwise, I think we're good to go. Zenkai, do you have anything else to talk about?
Not really.
Yeah, okay. So then we're good to go. Next week we're gonna be going over the USACO, which is in the future, right? So next week on Wednesday we'll go over the January USACO contest. Um, we'll go over the bronze questions probably, and maybe a silver question if we have time. But other than that, we're free to go. We'll stay behind for a couple minutes if you guys have questions. Otherwise, I'll just end the meeting in a couple minutes. Okay, I'm ending the meeting.